Okay, yeah, you have done your first homeworks, and I also asked you to go review those, and because we need this type of the content to go through the textbook, so we will supply the mathematical background for the big data study. Okay, so I expect you to solve some of the problems that you are on the borders on these earlier content. Okay, and next page. Next page. Next page. 어? 키보드에서. 현재부터. Okay. So I expect you to add your problems in Q&A, and so we can start to go through it in a short way. And I also supplied some of the earlier lecture of mine on those. But today, we will talk about the matrix decomposition. We will start from the matrix decomposition, and then we will cover the power method and Jordan canonical form or matrix functions and least square solution, etc. Okay, first, here's the references for those what we're going to try to cover. First, matrix factorization is a main technique of designing algorithms. So we start from the LU decompositions. Okay. I uploaded the lecture note before the class, and also I introduced some code for doing LU decompositions. Okay. Okay. LU decomposition can have several variations, including LDU or LDL transpose or Cholesky factorization, which is A is equal to L times L transpose. So, I gave you a homework, so you can try to find the LU decomposition of 7 by 7 matrix and solve a linear system of equation of that matrix by using LU decomposition. And most of you have submitted your answers in Q&A already. And you already gave the answer on those true-false problems, which I draw from the book that I have written, and the discussion has been started, and the reasons and counterexamples were given. We will try to finalize your discussions in a week. Okay, now we start the LDU factorization. As you know, the LDU factorization can be done by Gaussian elimination. If you do the Gaussian elimination, then we did this conjugate matrix. Then Gaussian elimination is the same as the multiplying the elementary matrix on the left hand side of the matrices. At the end of the series of Gaussian elimination, you will have the upper triangular matrix and another vector y here. Then this, if we have the if we analyze these elementary matrices, suppose there was no need of permutations of rows throughout the forward elimination on this matrix, then what that means is these are the product of elementary matrices is actually product of a lower triangular matrices. And inverse of that is also a lower triangular matrix, which can be written in this way. So, thus A matrix can be written as the so L inverse times A is equal to U, which means A can be written as the L times U, where L is a lower triangular matrix and upper triangular matrix. Actually, this is the whole idea of LU factorization, like this. So A can be written as a lower triangular matrix and upper triangular matrix. We can even make this the main diagonal of this lower triangular matrices are all ones. Okay. With that, solving the linear system of equation AX is equal to B can be split in the two steps like this. Solving the linear system of equation Ly is equal to B, and to find y, then substitute y to solve ux is equal to y to have the solution x by backward substitution. Easy. This so example shows how the algorithm works. If the elementary row operations and is taken, then elementary matrices can be found to be multiplied on the left like this. As you see, when you do the elementary, when you multiply the elementary matrices, then we will have the upper triangular matrix like this. Then product of this lower triangular matrix is also a lower triangular matrix, and inverse of each is also a lower triangular matrix. So L can be written in this way from here. Then matrix A can be written as LU. Then the forward substitution gives us the answer. Y is equal to, Y1 is equal to 1, and Y2 is equal to -4, and Y3 comes like this. Then use this to have X by backward substitution here. There is one free variable, so we choose a free variable T as for X4, then others will be followed to have the whole solution. This is the way. Okay, and there are other, after A, when we have A equal to LU, then we can split this upper triangular matrix U as a diagonal matrix D and the upper triangular matrix U, whose main diagonal entries are ones. So the matrix A can be split as a product of L lower matrix and diagonal matrix and the upper triangular matrix, whose main diagonals are all ones. Okay, these algorithms are called LDU factorization or LDU decomposition of A. Okay. Some matrix may not have LU factorization, but suppose now a low interchange is necessary during the forward elimination. In this case, this low interchanging elementary matrix altogether form a permutation matrix P, so that the matrix PA can have an LDU factorization. So, like what you see, if we have this type of matrix which do not have LU factorization, then we permute this matrix A first, then do the elementary row operation to have LDU factorization. So, and we can recognize that there are many LDU factorizations for one given matrix, as you see in this example. But if a matrix is invertible and if the permutation matrix P is fixed when it is necessary, then PA has a unique LDU factorization. If you give an order, then we can have a unique factorization, which gives the theorem like this. Let A be an invertible matrix, then for a fixed suitable permutation matrix P, the matrix PA has a unique LDU factorization. This is the theorem for the LDU factorization. And here is the proof. And we already proved the existence of LDU factorization for the given conditioned matrix. Then all we have to do is to just show the uniqueness So suppose there are two ALDU factorization for matrix PA, then we need to is show L1 and L2s are same, and D1, D2s are same, and U1, U2s are same. This is a direct in order to show this, we note three facts. The first, inverse of a lower triangular matrix is also a lower triangular matrix, and inverse of a upper triangular matrix is also upper triangular matrix, and inverse of a diagonal matrix is also diagonal. Using this property, we can easily compare the ij's entry of each of the matrix to find these entries are all same. Okay, this is a very simple proof that you already have seen. Okay, if an inverter matrix is symmetric, then this matrix, the A can have, if A is symmetric, then A is equal LDU. It should be same as A should be same as A transpose, which is this, which is U transpose times D transpose L transpose is equal to U transpose D L transpose, which is same as LDU. Then L and U transpose should be same, and U should be same as L transpose, which means this U should be same as L transpose. So we have LD L transpose. Okay, I asked you to do try to solve find the LU factorization of 7 by 7 matrix and solve the linear system equation to have the proper solution for the system of linear equations. Okay, these are the facts that I mentioned, and if they are lower triangular matrix, then product of A and B is a lower triangular matrix, and if A is an invertible matrix, then A inverse is a lower triangular matrix, and if AII is equal to 0 for all I, then main diagonal entries of A inverse is also 1s. And this proof was given in the ebook that I wrote, so you can check those proofs and properties from this book, CRM 3.61, and you must have seen it. But I tried to give you the proof of this theorem once more. Prove the product of two lower triangular matrices is lower triangular matrix. Okay, here we want to show AB is a lower triangular matrix. For this type of problem, I recommend you to have a intuition first. Try to multiply two lower or upper triangular matrix and see what is going to be. Then from this simple computation of a couple of examples, then you will see clearly how it works. And what we have to do is just in order to show the AB is a lower triangular matrix, all we have to do is look on the ij's entry of the product and see the super diagonal entries are all zeros, which means this ij's entry is 0 for the super diagonal entries. Here is actually proof. The proof for the upper triangular matrices. If A and B is an upper triangular matrix, then the product is also upper triangular. So if A and B are given like this, then C can be written in this way. All we have to show is Cij is equal to 0 for all I bigger than J. So yeah, I bigger than J. So lower the subdiagonal entries are all zeros. How it can be done? Here, the Cij, which is a summation of Aik, Bjk, like this, can be written in this way. We split it in the three parts: first part, second part, and third part, like this. Then, for all I bigger than j, we can easily show this part is 0. For all bij, which is for all j plus 1 is bigger than I. Okay. Anyway, we can from the give and also we can check 1 over these terms among these parts are all zeros. And similarly, for these entries, is the 1 over Aij or Bij's are 0 on each of terms here. So summation of all these are 0. So in any cases, this and this part are all zeros. So this shows Cij is equal to 0 for all I greater than Gj, which means the matrix C is an upper triangular matrix. Okay, the inverse of lower triangular matrix is also lower triangular matrix, and the matrix, actually we had Java code for this computation that you can use. So just take a look on it and find the LU factorizations, and for this matrix then can be found in this way by hand. But for the larger size matrix, you better develop a code to check to get the answers. Solving the linear system of equation when A can be factored like this, then you can solve easily to solve this Ly is equal to B to have y1 is equal to 2 and plug in here to get y2 value, and yc will come directly. Then plug in here y and to get xi's to have it. This is the algorithms. And with those background, we can go a little further. Matrix A can be written as the set of row vectors and set of column vectors like this. And when we have a matrix A, which is a lower triangular matrix like this, then inverse of lower triangular matrix can be found an easier way. We can illustrate the algorithm for finding the inverse of a lower triangular matrix. As you see, the inverse of the inverse matrix of A have the sub-diagonal entries has what? When A has 2 on A1, 2 on position, there's -2, 4, -4, 1 goes, -1 goes to 1, and 5 goes to -5, 3 goes to 3, like this. So there is a quite relevance. So we can easily find an algorithm to develop the inverse of a lower triangular matrix, which saves a lot of time for finding the inverse of matrix for when we have a lower triangular matrix. We can go further and further to fit out all this. When you multiply, you will see it's an identity matrices. And that's why we study the property of special matrices, including the inverse, the triangular matrices. And for the inverse matrix A has some diagonal entries different from 1, then we can define a matrix D. We can multiply D on A like this, which is a diagonal matrix whose main diagonal entries are the reciprocal of the main diagonal of A's. Then if we multiply, then the main diagonal of C are all ones here. And C inverse can be found in this way. So A inverse should be C inverse times D like this. But here important thing is finding the inverse of an upper triangular matrix A. In this case, it's going to be a lot easier because A transpose, inverse of A transpose is same as of A inverse of transpose. We already, for the triangular matrix, we've developed an algorithm to finding the A inverse effectively. So finding the inverse of transpose is just an easy way. So we only need to transpose it in order to obtain A inverse like this. So there are many things that we can do with it. Actually, we developed a code for doing this type of computations for. Okay, sorry. Okay. Okay, so I will show it later. And then the Cholesky factorization can be defined. in particular, if we have a symmetric and positive definite matrix A, then there exists a lower triangular matrix L, whose diagonal entry elements are all positive such that A is equal to L transpose, where L is the Cholesky factor of A. Like this. We had this, but without D, we can still have A is equal to L transpose when A matrix A is symmetric and positive definite. Is there anyone who knows about the definition of positive definite matrix? So positive definite matrix is a matrix that X star AX is always positive for any non-zero vector X. And with that property, the LU factorization can be improved in this way. In this case, we can easily solve the linear system of equation by forward substitution and backward substitution easily. Actually, I also showed how the Cholesky factorization can be done in here. Let's see. As you see here, as you see here, Cholesky factorization can be done like this. A matrix can be done as L times L transpose. So A matrix, this matrix can be decomposed by the L times L transpose. If you multiply this matrix times L transpose, then you will easily find this. And there are LD transpose algorithms. So anyway, okay. Here, so Cholesky factorization can be done. And the next step is block triangular decomposition. Like this. The block matrix can be splitted as a block lower triangular matrix and block upper triangular matrix like this. After that, what we need to study is the computation cost to do this kind of matrix factorization, and also sensitivity analysis of this linear system of equation and error analysis of Gaussian elimination. We do that on this, then we will continue to compare to the effectiveness and the cost with the other matrix factorizations. And this is what I gave you, the homeworks, then most of you already did. And if those who didn't do it yet, then you may do it before the next class to catch up. Okay, and also I have uploaded how to solve the linear system equation and how to find there's some other code as well for the background. And as you mentioned, you started the discussion, and we will conclude it. And the first one, for example, this last statement is false because sometimes we need a permutation before we do LU factorizations. So PA is equal to LU is possible, but sometimes A may not be able to decompose that as LU. And I was thinking to make a two-member team, and this is a tentative schedule, a tentative assignment. So you can switch your partners and let me know, so you can work together to solve the problems and discuss, and also for the project as well. The next matrix decomposition is Schur decomposition. Before we start the Schur decomposition and power method, if you have any questions, feel free to ask me.